Converting the secondary star configuration to a delta configuration will indeed eliminate the 30-degree phase shift. When connecting the secondary windings in delta, the phase shifts introduced by the star connection will be cancelled out. This results in a secondary voltage with no phase shift relative to the primary voltage. The impedance of a delta-connected transformer is the square root of 3, that is 1.732 times higher than that of a star-connected transformer with the same turns ratio. This means that the delta-connected transformer will have a higher voltage drop and lower short-circuit current capacity compared to the star-connected transformer. The power factor of the transformer will remain unchanged. However, the higher impedance of the delta configuration may lead to a slightly lower power factor for inductive loads due to the increased voltage drop. Delta-connected transformers generally produce less harmonic distortion than star-connected transformers. This is because the delta connection provides a path for third harmonic currents to circulate within the transformer, reducing their impact on the system. Delta-connected transformers can only be grounded on one side. This is because the neutral point is not accessible. If the delta-connected transformer needs to be grounded on both sides, a zigzag grounding transformer must be used. Firstly, the transformer's physical connections must be modified to change from a star to a delta configuration. Secondly, the applicable codes and standards must be followed when making the conversion. Thirdly, the transformer's rating and nameplate data will need to be updated to reflect the new configuration. Fourthly, the impact of the impedance change on the system should be carefully assessed. In summary, converting the secondary star configuration to delta configuration will eliminate the 30-degree phase shift. However, it will also increase the impedance and may slightly reduce the power factor and short-circuit current capacity. The specific consequences must be evaluated for the particular application. Considering the impedance change, the delta connection results in an impedance increase by a factor of approximately 1.732 compared to the star connection, assuming the same turns ratio. This higher impedance affects the transformer's performance in several ways. With higher impedance, the voltage drop under load increases. This means that the secondary voltage will decrease more significantly as the load increases, which may affect the performance of connected equipment, particularly those sensitive to voltage variations. The short-circuit current capacity is reduced with the delta configuration due to a higher impedance. The short-circuit current is inversely proportional to the impedance, so a higher impedance limits the current that can flow during a fault condition. This can affect the coordination of overcurrent protection devices such as circuit breakers and fuses. With the power factor, while the power factor of the transformer itself remains theoretically unchanged, the increased impedance can indirectly affect the overall system power factor, especially with inductive loads. The increased voltage drop due to the higher impedance can cause inductive loads to operate at a slightly lower power factor. Considering grounding, star-connected transformers provide a readily accessible neutral point, which allows for direct grounding on both sides if needed. Delta-connected transformers, on the other hand, do not have a natural neutral point. Grounding can be achieved on one side, but if grounding is required on both sides, a zigzag grounding transformer is necessary to create a neutral point. Using a zigzag transformer can be an additional cost and complexity. The reduction of harmonic distortion in delta-connected transformers is due to the circulating currents. Delta connections provide a closed-loop path for third harmonic currents, which are common in many electrical systems. These circulating currents effectively trap the third harmonics within the transformer windings, preventing them from propagating into the rest of the system. This can lead to a cleaner power supply with reduced harmonic distortion. The specific codes and standards include the National Electrical Code or NEC and IEEE standards. These codes and standards provide detailed guidelines on how to safely and effectively modify transformer connections. They cover aspects such as wiring methods, overcurrent protection, grounding, and labeling. It is crucial to adhere to these standards to ensure safety and compliance. The transformer's rating and nameplate data need to be updated to reflect the new configuration because the change from star to delta affects the voltage and current ratings of the secondary windings. The new nameplate should accurately reflect these changes. The system impact assessment is very important because changing the transformer configuration can have cascading effects on the connected equipment and the overall electrical system. A comprehensive assessment should include the following steps. Firstly, perform a load flow study. Use software tools to simulate the system under various load conditions to assess voltage drops and current flows. Secondly, perform a short circuit study. Determine the available fault currents at various points in the system to ensure that overcurrent protection devices are properly coordinated. Thirdly, analyze harmonic distortion. Use modeling tools to evaluate the impact of the transformer configuration change on harmonic distortion levels. Finally, verify equipment compatibility. Ensure that all connected equipment can operate within the new voltage and current parameters. In addition to the steps mentioned, several other factors should be considered when converting a transformer's secondary configuration from star to delta. Firstly, temperature-rise considerations. Delta-connected transformers may experience a different temperature rise profile compared to star-connected transformers. The increased circulating currents in the delta configuration can lead to higher winding temperatures. It's essential to verify that the transformer's cooling system is adequate for the new configuration. Secondly, inrush current considerations. Delta-connected transformers can exhibit higher inrush currents during energization compared to star-connected transformers. This is due to the absence of a neutral point that can help dampen the inrush. This can potentially trip over current protection devices or cause voltage dips. Thirdly, system protection coordination. Changing the transformer configuration affects the coordination of overcurrent protection devices. The higher impedance of the delta configuration means that the available fault current is lower, which can impact the settings of circuit breakers, fuses, and relays. The protection scheme must be re-evaluated and adjusted accordingly. Fourthly, insulation stress. The voltage distribution within the transformer windings can change when converting from star to delta. This can potentially increase the stress on the insulation, especially at the corners of the delta connection. It's crucial to ensure that the transformer's insulation system is adequate for the new configuration. If the transformer is relatively old or has been in service for many years, it may be prudent to perform insulation testing before making the conversion. Fifthly, neutral availability. Star-connected transformers provide a convenient neutral point for grounding and for supplying single-phase loads. When converting to delta, this neutral point is no longer available. This can affect the ability to supply single-phase loads and may require the installation of additional transformers or other equipment to provide a neutral. Sixthly, the economic considerations. Converting a transformer's secondary configuration can be a significant undertaking, involving labor, materials, and downtime. A thorough cost-benefit analysis should be performed to determine whether the conversion is economically justified. The analysis should consider the costs of the conversion, the benefits of eliminating the phase shift, and any potential impacts on system performance and reliability. Seventhly, the regulatory requirements. In some jurisdictions, converting a transformer's secondary configuration may require approval from regulatory authorities. This is especially true if the conversion affects the transformer's rating, grounding scheme, or protection system. It is essential to check with the local authorities to determine whether any approvals are required before making the conversion. Eighthly, the safety considerations. Converting a transformer's secondary configuration involves working with high-voltage equipment and requires strict adherence to safety procedures. Only qualified personnel should perform the conversion, and all necessary safety precautions should be taken, including de-energizing the transformer, grounding the windings, and using appropriate personal protective equipment. Ninthly, the documentation. All changes made to the transformer should be thoroughly documented, including wiring diagrams, nameplate data, and test results. This documentation is essential for future maintenance, troubleshooting, and modifications. Tenthly, the training. Personnel who will be working with the transformer after the conversion should be properly trained on the new configuration and its implications. This training should cover aspects such as grounding, protection, and troubleshooting. Converting from a star to a delta configuration has implications on voltage and current relationships. In a star connection, the line-to-line voltage is the square root of 3 times the line-to-neutral voltage. In a delta connection, the line-to-line voltage is equal to the phase voltage. As for current relationships, in a star connection, the line current is equal to the phase current. In a delta connection, the line current is the square root of 3 times the phase current. A star connection is suitable for providing both three-phase and single-phase power. Delta connections are mainly used for three-phase power distribution. A zigzag transformer is used to derive the neutral point. The zigzag transformer consists of 2 identical windings on each core, but they are connected in opposite polarity, allowing zero-sequence currents to flow freely, establishing a stable neutral point. You can use a grounding transformer to achieve the same outcome, but a zigzag transformer provides a better solution for harmonic mitigation. The effect of the change on inrush current. The inrush current is the transient current that flows when a transformer is initially energized. Delta-connected transformers typically exhibit higher inrush currents compared to star-connected transformers. This is due to the fact that delta connections provide a closed-loop path for circulating currents, which can amplify the inrush current. The magnitude and duration of the inrush current depend on various factors, including the transformer's size, impedance, and the point on the voltage waveform at which the transformer is energized. Higher inrush currents can cause nuisance tripping of overcurrent protection devices and can potentially damage the transformer windings. The change in impedance. The change in impedance is a key factor that affects the transformer's performance and the overall system behavior. The impedance of a transformer is the opposition to the flow of alternating current and is typically expressed as a percentage of the transformer's rated voltage. When converting from star to delta, the impedance increases by a factor of approximately 1.732. This increased impedance has several implications. Firstly, voltage regulation. A higher impedance leads to a greater voltage drop under load, which can affect the performance of connected equipment. Secondly, fault current. The higher impedance limits the fault current that can flow during a short circuit condition, which can affect the coordination of overcurrent protection devices. Thirdly, parallel operation. When operating transformers in parallel, it is important to ensure that the impedances are closely matched to avoid circulating currents and unequal load sharing. The change in harmonic distortion. Harmonic distortion is the presence of unwanted harmonic frequencies in the voltage and current waveforms. Delta-connected transformers generally produce less harmonic distortion compared to star-connected transformers. This is because the delta connection provides a closed-loop path for third harmonic currents, which allows them to circulate within the transformer windings and reduce their impact on the system. The reduction in harmonic distortion can improve the power quality and reduce the risk of equipment damage. The system grounding configuration. The system grounding configuration refers to the way in which the neutral point of the transformer is connected to ground. The grounding configuration has a significant impact on the safety and reliability of the electrical system. Star-connected transformers provide a convenient neutral point for grounding, which allows for direct grounding on both sides if needed. Delta-connected transformers, on the other hand, do not have a natural neutral point. If grounding is required on both sides, a zigzag grounding transformer is necessary. The choice of grounding configuration depends on various factors, including the type of load, the sensitivity of equipment to voltage transients, and the requirements of the local electrical code. The voltage distribution in the transformer windings. The voltage distribution within the transformer windings can change when converting from star to delta. In a star-connected transformer, the voltage is distributed evenly across the windings. In a delta-connected transformer, the voltage is concentrated at the corners of the delta connection. This can potentially increase the stress on the insulation, especially at the corners of the delta connection. It is important to ensure that the transformer's insulation system is adequate for the new configuration. The transformer's cooling system. The transformer's cooling system is designed to remove heat generated by the transformer's losses. When converting from star to delta, the transformer's losses may change, which can affect the temperature rise of the windings. It is important to verify that the transformer's cooling system is adequate for the new configuration. The cooling system may need to be upgraded or modified to handle the increased heat load. The transformer's tap changer. A tap changer is a device that allows the transformer's turns ratio to be adjusted, which can be used to compensate for voltage variations. When converting from star to delta, the transformer's tap changer may need to be adjusted to maintain the desired output voltage. It is important to consult the transformer's manufacturer to determine the appropriate tap changer settings for the new configuration. The transformer's overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the transformer from damage due to overloads and short circuits. When converting from star to delta, the transformer's overcurrent protection scheme may need to be re-evaluated and adjusted to ensure that it provides adequate protection for the new configuration. The overcurrent protection devices should be sized and coordinated to protect the transformer from damage without causing nuisance tripping. The transformer surge protection. Surge protection devices, such as surge arresters, are designed to protect the transformer from damage due to voltage surges caused by lightning strikes, switching operations, and other events. When converting from star to delta, the transformer's surge protection scheme may need to be re-evaluated and adjusted to ensure that it provides adequate protection for the new configuration. The surge protection devices should be sized and coordinated to protect the transformer from damage without compromising the safety of personnel or equipment.